Thank you for the very kind invitation to speak today. I'm going to talk about representational drift. So we're moving from whole brain down to local circuits. Representational drift is the experimental observation that even when animals have very stable behaviors that are stereotyped and stereotypical, the patterns of neuronal activity that are thought to underlie these behaviors continue to change on timescales of days and weeks and even months. And this is surprising, but it's also disturbing on some level because a very fundamental tenet of systems neuroscience is that every mental state and every behavior is driven by a pattern of neuronal activity. There's nothing else. So if the behavior is stable, how is it that the activity is not? So what am I talking about? This isn't working, so I'll just use this. Use this. Nope, I cannot advance at all.
Did you click your screen?
If I click this,
make an active presentation.
Let's seem to advance. To click me directly on this.
Yeah.
Okay. There we go. All right. So I'm gonna. It's okay. Slightly more effort intensive. It's okay. So what am I talking about? Here's an example. So this is from calcium imaging in mice. These mice are just running back and forth on a linear track. It's a familiar environment to them. So the x-axis here is position, the y-axis is the identity of the cell, and you're looking at the activity of the cell. Red is more active. This is calcium imaging. So when you order the cells according to their preferred location, you have this nice tiling of space. This has been known since the 70s. What was not known is the fact that if you look at the very same cells on subsequent sessions, so this is after 5 days and up to a month in this case, this pattern of activity changes. Okay, it gets smeared out. And this smearing out or this decorrelation is due to changes in single cell activity. So some of the cells drop out of the code, that's the increasing blue. Other cells pop into the code, and you have changes in levels of activity and also in the tuning of the cells. These are place cells, their place field can actually shift. So this is what I want to call the first salient characteristic of drift. It's this smearing out of activity. But there is another salient aspect, which is that if you reorder the cells according to their preferred location on any given session, say on day 20, you once again obtain this very nice tiling of space. And in fact, you can see that the structure of the population activity is largely preserved. Okay, so despite these ongoing changes, the population structure is stable, or if you will, the neural manifold is stable. So this, I'm going to call this the second salient characteristic of drift. This is seen not only in hippocampus, but in many different areas. I'll show you some more data later. And so there are several questions you could ask about this drift. Okay, one is, what is the mechanism driving it? Another would be, given that it's happening, how do you maintain stable behavior? And a third might be, is it good for something? Is this happening for a reason? I'm going to focus entirely on the first question. What are the mechanisms underlying it? And so my talk is going to be about these two aspects. First, I'm going to tell you, okay, what is causing this drift? And I'm going to suggest, and I hope convince you that if you have a system that's just continually learning and encoding information, this is going to happen. Okay. And this is going to be a relatively brief part of the talk. It's published work. Then I'm going to move on to unpublished work, which I'm very excited to talk about. And that's going to discuss what are the mechanisms which can somehow contrive to maintain the population structure in the face of all this ongoing, in the face of all these ongoing changes. And the answer is going to be the randomness in the network structure, which sounds weird, counterintuitive, but hopefully by the end of the talk, you'll agree that that makes sense. So let's go to the first point. The idea is extremely simple, so you can really understand it in terms of cartoons. So I'm doing an experiment, and I'm recording from a number of cells. This would be one of those cells, and of course, the output of the cell just depends on the pattern of inputs and the synaptic weight matrix. So in this case, it's receiving two strong inputs on two very strong synapses. Its output is strong. That's on one session, and then some time elapses, 5 days, for example. And on a subsequent session, the animal's doing the same thing. It's at the same position on the track. It's receiving the same visual input. So the pattern of activity is the same, the presynaptic pattern, but for some reason, the synaptic weight matrix has changed. Well, here you can see it's receiving less drive It's not surprising that it's going to fire less. See, it's utterly trivial. Now, this could be due to some synaptic volatility. It's known that spines just appear, they disappear. This happens a lot in the hippocampus, but throughout the cortex. Or it could be some plasticity or learning, right? Synapses change, they become depressed or potentiated due to the storage of information. In the case of the hippocampus, it's known the hippocampus is involved in a lot of different types of memory, including spatial memory, episodic memory. So that would make sense. At the population level, just to hammer home the point, so I'm going to be observing some population of neurons. So the black ones here are active, and they're receiving input from some other upstream neurons. And I'm thinking of a feed-forward architecture here. So I'm specifically thinking of hippocampus. I'm thinking of this as CA1, let's say, and this could be CA3 or entorhinal cortex. And I'm only showing you one connection. There are many, of course. And so this pattern of activity is eliciting this output pattern. And in between sessions, there's some changes to the synapses. See, this synapse just disappears, and this one appears for some reason. And then in a subsequent session, by virtue of those changes, the pattern of activity has changed. So if there's just some rate of synaptic turnover in my simple model here, that's going to lead to a continual decrease in the correlation of this pattern of activity that I'm observing in agreement with experiment. In the case of Hebbian plasticity, it's slightly different. The effect is the same. So once again, I'm observing a pattern of activity. But now, in between sessions, I'm assuming that there are other patterns of activity. So this gray one is different than the black one. And these patterns of activity, they are encoded in my network through a Hebbian plasticity rule. Okay, this is a feed-forward network. So these would be hetero-associative patterns. Right, I'm associating an input pattern with an output pattern. And these dashed boxes show you the overlap of this pattern with the one I observe. And that's important because the overlap gives me the degree of interference, which tells me how much drift I'm going to see. Because that means I'm interfering with the synapses that matter for the pattern I'm observing here. So with some Hebbian plasticity rule, a simple one would be, well, if pre and post are different, depress with a particular probability, call it P minus. If pre and post are both active, then potentiate with a probability P plus, something like that, stochastic process, and it changes the synapse so that on a subsequent session, once again, I obtain a different pattern of activity by virtue of having encoded other patterns in my network. Right? So if I have some rate of encoding in my network, that's going to cause a continual decorrelation in my output pattern. All right. Well, that's fine. I mean, you could imagine if you have a large network and you just want to encode a couple of things in it, that this doesn't have to happen. So for example, imagine that this is the pattern of activity I'm observing in experiment. And the only other thing this network has to do is encode, say, this red pattern. Then I could separate them in such a way that there's no overlap between these patterns. I could even maybe do it with another pattern. All these patterns have 6 neurons. So that's my constraint. But at some point, I'm going to get some overlap. I'm going to have some interference. It's unavoidable, and so on. So it's not just that a Hebbian mechanism can lead to representational drift. If you have it in a network which is operating at capacity, which is continually encoding until it hits its capacity, it has to happen, right? As shown in this cartoon. So you can take this very simple Hebbian mechanism, right? It is not just in a cartoon, but in a self-consistent model. And because it's so simple, you can also quite easily fit it to data. So this is an example, and I'm just giving you an illustration. I'm not talking about any of the details. So we built a spiking network of integrating fire neurons, leaky integrating fire neurons for CA1, receiving untuned and spatially tuned inputs from CA3 and entorhinal cortex, and using this type of Hebbian plasticity mechanism by continually encoding patterns in between sessions, or with synaptic turnover. You can do both, right? They're effectively the same at this level. You can generate these types of plots, which are reminiscent of experiment, and you can, in fact, even fit data quantitatively. So this sort of result is consistent with both synaptic volatility and Hebbian plasticity. But without going into detail, there are other very interesting findings that are only consistent with the Hebbian plasticity. So for example, if you take mice and you familiarize them with an odor, and you take two groups now, in one group, you give them that odor more often than the other, you find that the group that smells that odor more often has less drift. So you can stabilize the representation of the odors by increasing the repetition rate. Well, this can be explained with a Hebbian mechanism and not so easily with synaptic volatility. Similarly, it's found in hippocampus that if you look at the drift of place cells, the amount of drift in the overall activity level just depends on the total elapsed time between sessions. That's all it depends on. Whereas the amount of drift in the tuning depends on how much time the animal spends in the environment. And again, this is very consistent with a Hebbian mechanism, but not synaptic volatility. Okay, so I hope to have convinced you on the cartoon level, at least, that representational drift is consistent with a system that's just continuously encoding patterns. I want to move on to the second salient characteristic of representational drift. Now, I showed you an example from hippocampus, but this is seen all over the brain, all over the cortex at least. Here's an example from motor cortex. These are monkeys now that are moving a joystick in one of 6 possible directions. So you can use a low-dimensional projection algorithm to look at the neuronal activity in 3D on 2 different days, let's say, day 27, day 43, and you see completely different patterns of activity, suggesting that the underlying neuronal representation has changed. But if you're clever, and these people were, you can reorient these projections in such a way that you see, actually, the neural manifold is identical. So there have been some ongoing changes, but nonetheless, the population structure, the neural manifold is stable. Here's an example from auditory cortex. So here you're looking at different sessions on different days. The cells are ordered according to their preferred stimulus on day 5. X-axis is now not space, but stimulus. These are pure tones and then more complex tones. Y-axis is still cell identity. And you can see this nice response profile, which if you go back or forward in time gets smeared out. But if you reorder the cells according to their preferred stimulus on any given session, you see that structure is always stable. So it's this neural manifold, which is stable in the face of ongoing change. And yet another example, which is particularly striking to me, it's going back to the hippocampus. So these are from 5 different mice. That's the 5 panels, 5 different mice. And you see these colors. The colors correspond to different 2D arenas. And these are morphed environments. They morph from a square to like this double square thing. And you see now in this low-dimensional projection, again, now in 2D, these lines. These lines are how the representations change in time. This is this first salient characteristic. This is the drift in time. The interesting thing is that if you look at the representations of different environments, they all move in the same direction in such a way that the distance between the representations of any 2 environments is fixed in time. Even though they're all changing, that distance between the representations is fixed. Okay, so how can we understand this? So first I want to take a more geometrical approach to this. So I want to go back to this data. This is the hippocampal data. And this activity here, this is the activity of cells averaged over a session. I can take a spatial bin, say this purple one here, and get a vector of activities. Now, this is just some vector in the space spanned by the activity of all the cells. So in this case, it's 178 dimensional. It's just some vector. Now, I could look at a different position, say this cyan position. The pattern of activity is different, and therefore I'm going to get a different vector. And I can measure the angle between them, let's say. Now, if I take a closer position, say here, then the patterns of activity are more similar, and therefore this angle will be smaller, okay? Now, the fact that there's drift means that if I look at this purple position on a different day, say here, well, this pattern of activity is different. That means that this vector has been rotated by an angle, let's call it alpha drift, all right? However, now I'm going to leverage this second salient characteristic of drift, which tells me that, well, this activity actually has the same structure. So whatever this pattern happens to be, it's been rotated. Here it is. I'm just resorting it. It's the same activity. If I look at this cyan position here at a later time, its angle with respect to the purple one is actually very similar to the previous one, which means that what drift has done is any given output pattern is rotated it. But if I consider the similarity between, say, two different representations, they get co-rotated. That's what that means. So these angles are just about the same. Okay, so pairs get co-rotated, but that's true for any pairs, right? So if you assume that your neuronal activity is sort of constrained to a low-dimensional manifold, and it always is, as far as I know, it just means the whole manifold's been rotated, okay? So you have these preserved pairwise similarities, which imply a manifold rotation, which implies that the geometry of the population activity has been preserved. These are all equivalent statements. So what is the mechanism that does this? Right? That's what we want to know. Is there a simple network or dynamic mechanism which can reproduce this result? Because it seems quite special. So let's start simple. We can take a simple binary feed-forward network. So here I have a sparse binary matrix W. I have an input vector X in, which is just zeros and ones with some sparseness, call it S. I think it's, if I show you simulations, S will be 20% or something like that. And then my equation for the output just looks like this, where the sigma is chosen in such a way that the output sparsity is equal to the input sparsity. That's it. That's all I want to do. I'm going to take, and the matrix looks like this. It's just a random matrix. And I'm going to look at some input stimuli which have a linear dependence, similar to the sort of sensory input the animal would get on the linear track. So X here is stimulus identity. These are all the different stimuli. So I can look at my two different input vectors. I'm just going to pass it through my random network. That's all I'm going to do. And I get this output. Random network, disordered output. But now I'm going to order the cells according to their preferred stimulus. And I get this. You can look at a different input topology. So here we have, this network is in fact 1,000 dimensional, but I'm going to constrain the inputs to lie along this torus. And this is just a low dimensional projection, principal components, of this very high dimensional structure. And I pass it through the same network. And if I'm not smart and I just use some arbitrary projections, I get these blobs. But if I use PCA, let's say, I have a torus in the output as well. So if you look at the relationship between input similarity and output similarity in random networks, you find that there's a lawful monotonic relationship, which is that input similarities are preserved in the output in random networks. So I don't know if you think this is trivial or magic. Usually people are divided, they go both ways. And the future slides are going to be pretty similar to this. So usually it's trivial or magic. The people who think it's magic by the end of the talk, usually they think it's trivial. So, which I don't know if that's good or bad, actually. Yeah.
So you mentioned something like the last, when the sorted.
Yes.
That, they are sorted by some preferred.
The preferred stimulus. So I look at what stimulus generates the maximum response, or what actually the center of mass of the response across stimuli.
Right.
Yeah.
Okay. All right.
Yeah. All right. But so that's the relationship between inputs and outputs in random networks. But I'm interested in drift. So, and I told you I think drift is due to changes in synaptic connectivity. So I'm going to do that. So now I'm going to simulate time discretely. And I'm going to simulate differences between sessions. So I go from one session to the next, and I do that in the simplest model possible, just rewiring connections. So this would be like synaptic turnover. There's just some changes in synapses. And the way we do it is we randomly rewire some fraction of synapses. And what I'll show you, it's 20%. And I'm going to use the same input stimuli. Okay. So here, sessions 1 through 4, I just randomly rewire 20% of the connections from one session to the next. And you see this smearing out of the activity. This is this first salient characteristic of drift. But I can reorder these according to their preferred stimulus. Well, not yet, sorry. Right. If I look at how much rotation I get as a function of the rewiring fraction, you see it's significant, even when I just rewire a little bit. So this is giving me this alpha drift. This is the alpha drift here. So outputs get rotated when I rewire. But now here I see if I reorder the cells here according to their preferred stimulus, I once again obtain precisely the same network structure, or close to the same network structure. And that means that the similarity between pairs is being preserved, or the words that we're using, the names we're using is the response vector difference and the response angle difference. The response vector difference is large. That's the amount of drift. The response angle difference is very small. In fact, you can see here, if you order according to any given session, it's orders of magnitude less. And this means that the neuronal manifold is preserved, topology is preserved. So similarities are preserved, or if you will, the neuronal manifold is preserved in random networks under rewiring. I didn't do anything special. So this is just rewiring. What about Hebbian plasticity? You can play the same game, but now from one session to the next, what I'm going to do is I'm going to encode a number of patterns with a rule that says if pre and postsynaptic cells are coactive, remember everything is binary zeros and ones, I potentiate, I make a connection with probability P plus. If the activities are different, I remove that connection with probability P minus. Now in this case, I start off with some initial network and I start encoding patterns in it until I reach a steady state. Okay, until the statistics of the network have reached a steady state. And then I start applying my linearly dependent stimulus to it. And when you do that, you see this, once again, this relationship between input and output angles, the similarities, that holds. And now I'm going to model the changes from one session to the next, I'm going to encode a number of other random patterns, okay? And I do 100 patterns in this case, and I find once again that the vector difference is much larger than the angle difference, meaning that once again, the neuronal manifold is preserved, all right? And this is actually quite robust to parameters. So these are the learning rates. This is how easy it is to depress or potentiate. Here you see a large rotation. So this is the angle change. This is a large overall rotation. White here means a very small difference. So you can see it only really breaks down up here when the learning rates are very large. In that case, if you look at the out degree, it's highly skewed to large out degrees. And that means there are certain cells in the input layer that are projecting very broadly to the output layer. And that means that even very different input patterns are getting projected to similar output patterns. And that's when it breaks down. So the storage of random patterns via Hebbian learning in networks preserves similarities as well. All right. I've only talked about feed-forward architectures. So what about recurrent architectures, which are very common in the brain? Not so much in CA1, but I showed you some other examples where they would be very relevant. So let's look at a recurrent network. Now, in this case, I'm still providing the system with the same sort of linearly dependent inputs, but now I'm not going to touch the feed-forward connections. They are fixed. They're just some random projections, okay? Now I have these recurrent interactions between the cells, and those are the ones I'm going to change to model drift from one session to the next. Now, for this model, which I'm going to take to be, at first, a very simple linear model, I'm going to take these M's not to be binary, but to be Gaussian random variables. And this is for ease, conceptual ease, because I'm going to take them to be Gaussian with zero mean and with some variance, which allows me to control the spectral radius, okay, of the eigenvalues. And now to model changes in M, we're just going to update the weights according to an Ornstein-Uhlenbeck process, which maintains the distribution of weights while shuffling them. And this is the result. For the linear model, the relationship between input and output is the identity. If you look at the overall rotation, it depends not only on the amount of change I make, so the x-axis is the amount of change that I make in the network, but it also depends on the spectral radius, which essentially measures how close the system is to an instability, okay? in any case, whatever the spectral radius is, you can see that the amount of rotation here, the amount of overall rotation, is always much larger than the change in similarities, meaning that once again, this neuronal manifold is maintained. You can add a nonlinearity. Here's a rectifying nonlinearity, and you achieve the same result, even cleaner in this case. So changes in recurrent weights preserve similarity in random networks. So if you have a random network, magically, whatever topology you have in the inputs, it maintains it in the outputs. If you start to change the network structure, either through rewiring or through learning, all it does is it rotates. It rotates whatever structure is there, but it doesn't destroy it. Why is this the case? Okay, so the reason that this works is described in a mathematical theorem from the 80s. And these guys, Johnson and Lindenstrauss, asked themselves the following question. Imagine I have some data in very high dimensional space, so the dimension n, where n is very large. And I look at a data pair, 2 data points, okay, u and v. And I just calculate the Euclidean distance between them here. So they asked, can I find a mapping is there a mapping from this high dimensional space to a lower dimensional space? So k is less than n, could still be very large, but it's less. Where I look at the same data points, these are the remapped data points, f of u and f of v, and these are the distances between them. So they asked, can I find a mapping such that these distances are nearly the same? And why would they care? Because they were interested in data compression. So if you have data in a very high dimensional space, you can project it to a lower dimensional space. And if you maintain distances between the data points, you've maintained the integrity of your data, right? This is used in all devices, I think, this concept. So it's a very important data compression result. And they found that, yes, you can do it. One way of doing it is just using orthonormal random projections. If you do that, you will ensure that these distances are within this small parameter epsilon that scales like 1 over the square root of k. So in all the examples I've shown you, the projections in the network were very close to orthonormal random projections. In the case of the binary networks, if you have binary vectors in a high dimensional space that are sparse, they are orthonormal, or very close to it. And if you have Gaussian vectors in high dimensional space, of course they're orthonormal, right, in the limit. But we can test this more directly in our model. So far in the model, the input and output dimensions have been the same, 1,000, let's say. So now I'm just going to reduce the output dimension, and the result should deteriorate, right? And that's what happens. So if you look at the ratio of the vector difference to of the angle difference to the vector difference, which tells you how well this manifold is maintained, you can see it gets worse and worse the smaller the output dimension is, from 1,000, 110. So let's look at 0.5 rewiring fraction, let's say. And if I plot those 3 data points, you can see they go along this line, which is precisely just 1 over the square root of the output dimension. So the behavior of these types of networks really is well described by this theorem. Okay, I've spoken for 28 minutes, which means I have some more time, right? How much time do we have? 40, you said?
45 in total. So
45, okay, so I can really go slow. In fact, I can go so slow I can take a sip of water. All right. So there's this very old result. I guess it's not new at all. There's this very old result which explains why, if you want to maintain neuronal manifolds in the face of ongoing changes in random networks, you don't need to do anything. It's a property of the random network. However, circuits in the brain are not random, so that seems to pose a problem. But the idea is that from the perspective of any particular pattern of activity that you're observing an experiment, so I have the mouse in a linear track, I'm observing the response to that experience. From the perspective of that activity, all of the other structure in the network, which is due to the encoding of other episodes unrelated to that, that's going to look random if the input is high dimensional enough. So you have a lot of structure in the network, but it's going to look random or pseudo-random. That's the idea. That's the hypothesis. But we can test it more directly, actually. Not in the animal. That would be very hard. But we can do it in this type of network. So this is an artificial network. This is known as a convolutional neural network. This is sort of a precursor to your large language models. And this type of network, which has been around for 10, 15 years, is built for image categorization, image recognition, and it's loosely inspired on by the mammalian visual system. So you present the system with an image, and there's a series of layers. This is a deep network. You can see there's a convergence. There are a number of nonlinearities. There are also convolutions, which is what gives it its name. Convolutions are filters. And when you train this model using stochastic gradient descent, you train also these filters. And what you end up getting, at least in the early layers, are filters that look very similar to retinal receptive fields of early visual cortex, which is what made people, at least to begin with, very excited about these models for understanding something about the mammalian visual system. Be that as it may, the way these things work is you have a very large training set. There's a set called ImageNet of 14 million images now. For this ResNet 18, which is the smallest of these types of networks, we use Tiny ImageNet, which is only 100,000 images. So you train the network on these 100,000 images, you make tiny changes, and it's a very long process. And in the end, you have a system which gives you an output. And it tells you, it categorizes the image that you present it into one of 200 possible categories. Right? That's how it works. Now, what we want to do is we want to train the network to where its performance saturates, and then we want to continue to train it so that its performance does not saturate, but so that the internal representations continue to change, just as in seen in rodents. And what we want to do is we want to see how the topology of the internal representation changes over time. Right. So to do that, we need images that have a very well parameterized topology. And if you take a whole bunch of images from ImageNet, they don't. They're very complex, high dimensional things. So we use this this custom-made data set by Santi Galeya, who's working on this project, where he parameterizes the images in a very simple way. So we have camera angle, which lies on a circle. There's hue, which is color, that also lies on a circle, color wheel. And then there are other ones like light and size, which would lie on a line. So we take an image set, which is the convolution of the color and the angle. And when you convolve those, you get a torus. So we hope to see a toroidal representation of this sort of umbrella type data set. Yeah. And you can calculate the angles between all these images quite simply. Okay, so we train the network. So the x-axis here are called epochs. So in this field, each epoch, you have a batch of images, in this case, 100,000 images, and you show the images to the network and you apply, using stochastic gradient descent, you make very tiny changes to the connections and also to the filters. And over the course of, say, the first 100 epochs or so, you see the performance of this thing increase. There's a training set and a test set. The curve for the training set would reach 100%. So if you train it on images, it always categorizes them correctly. The test set are images it has never seen, so that's why it's not 100%, but it's a third of the time, which is pretty good considering there's 200 categories. It's down here is random. So that's the learning phase. And usually when people use these models, they would stop and just use it. Okay, but we're continuing to train it on the same data set. We're just randomizing, we're reshuffling the order of the images. And we want to see what's going on inside the network during this ongoing training. That you've seen already. Okay, so we use this nonlinear low-dimensional projection technique, UMAP. You can look at the topology of the input data set, which is this, right? This is not the data, this is yeah.
Do you mean by shuffling the images?
So we have 100,000 images, say, of all different categories. Just take that set, reshuffle it, and train the network again.
So you're changing the order.
Changing the order of the images, yeah.
But the images and the labels are the same.
The images and the labels are the same, yeah. But reshuffling was enough to induce changes in the connectivity. Yeah. So you do have this torus-like structure, and you can see how both color and angle are represented on this. All right, so now we can look at all the different layers. And here I'm showing you the relationship between the input similarity and output similarity as a function of layer in the network. And I'm also showing you the UMAP projection of the representation in layer 2. And you can see, indeed, it's a torus in layer 2. In deeper layers, it's not necessarily torus because the representations get more abstract. But here it's definitely a torus, and you can see the representation of both color and angle. And then we can look at a different point in time. So look at 3000. The representation it's still there, but it's been rotated, and you can see that the phase, if you will, of the representation is completely shifted in terms of color and angle. But nonetheless, this looks very similar to what is seen in the random networks. And in fact, if you look at the vector difference and the angle difference, the vector difference here is always much larger than the angle difference. Okay, once again, meaning that, I mean, this is just a restatement of what I just showed you. This is just more quantitative. But the representation in this deep network, as we continue to train it, and its behavior is not changing, this representation is just getting rotated, right? Which is exactly what happens in random networks. And let me just emphasize, in no way, shape, or form could you ever consider the structure in this network random. It's not, it's very far from random. It is categorizing images. Nonetheless, it behaves as if it were random. Okay. So the focus of the meeting was multiple scales, I believe. So I thought I should put a slide on multiple scales. Multiple scales are very relevant for representational drift, although the work I've talked about hasn't directly addressed it. But let me just point out, and this is all relatively low-hanging fruit because it's a new field, right? This field had to wait for the advent of technology which allowed for stable recordings over very long timescales. That didn't happen until about 10, 15 years ago. So, within a week, you could read all the relevant papers in this field and start making important contributions. So one thing I didn't show you is that drift occurs already over the timescale of minutes. So this is from a paper showing the x-axis here, and these are mice that are running in some environment, doesn't matter the details. This is mobility time. This is the amount of time the animal actually ran around in that environment. And the color on the dots just tells you the time difference between the recordings where they looked at the patterns of activity. It doesn't matter. What you can see is that the more the animal ran around, the more the representation changed. And this happened on the order of minutes, okay, to hours, let's say. But what I showed you previously, that was on the time scale of days and weeks. So there are vast spatial scales here, temporal scales, also spatial scales, I'm getting to that now. In terms of spatial scales, of course, in all the experiments people have looked at, it's known that representations are distributed across the brain. So when addressing this issue of how can behavior be stable in the face of all this ongoing change, people are thinking multiple areas. What about the downstream areas? What are they doing? Now, how are they changing? So one idea is that, if you look on the left, one idea is that they might be changing in a way commensurate with the upstream areas. So maybe like the readout areas are changing along with the upstream areas in such a way that the readout is always the same. So you have some co-evolution there. So you might have some co-drift in downstream areas in such a way that these changes are not a big deal. Another possibility is that you might have a lot of change in early areas and less change in downstream areas in such a way that you could stably read out, say, the areas right before you make a motor output. And there's earlier work which suggests something which goes along these lines. So now I can conclude. So I wanted to tell you two things. First, that this sort of drift which is seen is actually inevitable in networks that store memories at capacity, which I think is the case, certainly for hippocampus. Hippocampus is involved in episodic memory. You remember coming here this morning. You didn't have to exert any effort to do that. Your hippocampus just takes snapshots of your life, whether you like it or not. So it's continuously encoding information. So it's almost certainly operating at capacity. I guess you could make a similar argument for other brain areas. And then what I showed you is that, at least in models, neural manifolds are maintained during drift through random or quasi-random projections in network models, including in these convolutional neural networks. Which suggests that you don't need anything special to get that. You get it for free, for whatever that means. So I want to acknowledge Bastian, who did most of the work, and Santiago, who worked on the deep networks, and Gabe as well. Thank you.